Hello and welcome to the second video under coordination compounds. So why did we need coordination compounds theory, that is the crystal field theory? It's because of the limitations of the valence bond theory that is proposed. Let us look into the limitations. The valence bond theory could not explain certain things, which are the pairing of electrons that occur in strong ligands. It could not explain the color of compounds that are formed via transition metals. It could not explain the nature of the ligands that are strong or weak ligands. It could not justify the reaction rate or the structure of the complexes which are very complex, such as Cu, NH3 whole 4, 2 plus ions, for example. It could not give away the reason for the magnetic properties, that is the paramagnetic or the diamagnetic properties of the complexes. Moving on to the nature of ligands, that we saw that VBT could not explain this nature of ligands, but CFT did explain. Nature of ligands are of two types, strong and weak ligands. Strong ligands are the strong field ligands which produce larger crystal field splitting, which causes it to have low spin. The delta O here is greater than P. Then coming to the weak ligand, we have lesser splitting compared to the strong ligand, which causes high spin in the crystal field. Here delta O is less than P. P is the pairing energy. On the top you can see a series of ions. This is the series of the strength of ligands. The least from iodine to the highest in CO. Moving to CFSE, that is crystal field stabilization energy. Let's not confuse it with crystal field splitting energy because it is different. Now we are studying about octahedral and tetrahedral compounds. So we'll look into the formula of these two. Basically, crystal field stabilization energy formula for octahedral would be minus 0.4 into n of T2G. N is the number of ions in T2G or electrons in T2G plus 0.6 into n of Eg. Whereas in tetrahedral, the formula stays the same, but the minus exchanges with plus here from 0.4 to 0.6. You can find the CFSE of all the d orbital, like from d1 to d10 all the way, and you will get a table in octahedral that repeats itself after d5. Like for example, if I tell you d1 is minus 0.4, then going to if going in series it goes to minus 0.8, minus 1.2, minus 0.6 and 0. d5 is 0. Now we repeat again from d6 to d10. It's the same series again, like minus 0.4, minus 0.8, minus 1.2, 0.6 and 0. Whereas in tetrahedral, again it's the same way. After d5 it repeats itself. So it goes like minus 0.6, minus 1.2, minus 0.8, minus 0.4, 0, that is d5, and then again it repeats to minus 0.6, minus 1.2, minus 0.8, minus 0.4, 0. Here you can see the table basically is opposite of the table that we wrote for octahedral. Moving to the spin-only magnetic moment. You can find the spin-only magnetic moment using the formula of whole root of n into n plus 2, where n is the number of unpaired electrons. You can get questions like calculate the CFSE of the compound such as Fe2 plus, which has Fe2 plus. So we know that the atomic number of Fe is 26. So the number of Fe2 plus would be minus 2, that is 24, and then the last d orbital, that is the 3d orbital, will have 6 electrons. So now if we put it into a d orbital, if we fill each electron in a d orbital, that is 6, then we'll have 4 unpaired electrons. So the n over here becomes 4, which makes the formula whole root over 4 into 4 plus 2, which is basically equal to 4.89 bm. Bm is the SI unit of spin-only magnetic moment. That is it for this video. We'll come back with the next video on coordination compounds soon. Thank you.